you guys, and thank you for coming here. I know there are plenty of very interesting talks at this same time, so I really appreciate it that you took the time to come here. So today we're gonna talk about synchronous and asynchronous servers and see how they perform in different environments. But first, who am I? I'm a software engineer. I'm working at Skyscanner. I love Python. I'm organizing one of the local meetups from Python, PyDCN. If you ever are here in Barcelona and want to send a talk, please do. We really appreciate it, especially for people from abroad. I was a sysadmin for a long while, but now mainly I work on backend systems. And you can find me at Jordi Soucheiron. This talk and all the code samples are available in this link below. I don't know if you can see it. It's bit.ly/Jordi sync. You will have everything in GitHub and then all the slides, so if you want to ignore me and just read it, you can get it there. So, what are we going to talk about? First, I want to start by introducing how do the synchronous and asynchronous models work, especially in Python. Then we will see what is expected from these systems and how do we expect them to work. Then we will do some real benchmarks and then we will revisit our assumptions and get some conclusions around it. So how do sync systems usually work? Basically what we do when we have sync systems is, generally what we do is we put one worker per CPU or thread, and each of these workers will handle one request at a time. So when you have a request, it will take ownership of that thread, and it will run from the beginning to the end. If we lose the control of this thread, it's because the kernel has removed that from us. But no other request can actually get in the middle of that. So we always know that all the context is owned by us at any given time. So if we look at this particular code, we will see how we will start with request one. We will start running app logic. And then when we're waiting for I/O, we will do a syscall. And when we're doing this syscall, the kernel will remove the control from us. And then we will start running another request on the CPU. And then when the kernel decides, we will get back to the request one. So the fairness of our execution path will be decided by the syscalls that we make and the kernel whenever he decides that we don't need that CPU anymore or that another process needs it. On the other hand, when we have asynchronous servers, it works in a very different manner. We usually just have one worker per CPU, and the only bottleneck that we have when we're running code, and the only thing that decides when we switch from one request to another is our code. So basically, when we have an await in the middle of the code, the reactor, the I/O loop, or whatever we have that is handling that, will be the one deciding which is the next task that will get the CPU. But if we don't do that, the same request will be kept there forever, unless we release it manually. This is a good and a bad thing. It gives us more control. But on the other hand, it also means that we won't have the kernel applying fairness principles to this. So if we add a call that does a busy wait or something like that, like Nathan was explaining a bit before, we will end up in a situation where all the other requests are blocked in there, and we won't be able to see any results. And this is really, really bad. So for the benchmarks that we're gonna see now, we will have the following environment. I prepared 3 Docker containers. The first one is a very simple HTTP application. Then we have a Flask application, and an Nginx container that will have static web pages. This Nginx container is using OpenResty, so it has a Lua engine on top of it, so it will be slightly slower than the usual Nginx. To perform the benchmarks, I'm using WRK. This is a benchmark stressing tool. It talks HTTP to the servers, and it will give us metrics on how the servers perform. For this test, I used 2 threads from 100 to 10 connections, depending on the test, and all the tests have been running during 30 seconds. To gather memory and CPU usage, I used overstats, and it's been tested in my laptop, so these are the specs. So let's start with open resting. Open resting will add the capability of adding echoes in the middle of the locations here in Nginx. So what we can see is that we will be able to have different locations that have different delays. So if we access to location slash 100 milliseconds, we will have a sleep for 100 milliseconds and then we will return the result. This will make it easier for us to test with the same container different delays that our dependencies may have when they are answering. So with these, we will test how the Flask application that we have and the open AHTTP application that we have behave when our endpoints have different response times. And we go all the way up to 1 second to see what happens if we have a really slow dependency. So let's go with the Flask container, that it's probably what you're more used to. It's a very simple Docker file. How many people here is used to Docker? Or good, then I don't need to explain this, basically. That's great. So basically, we're running Unicorn with 100 workers, and we have Flask started by this. Nothing really fancy here. We will have two endpoints. The first one has an I/O bottleneck, so it will go to the Nginx container that we have. And depending on the delay get parameter that we pass, it will take more or less time to get a response. And we're using requests to gather this data from Nginx. The CPU bottleneck, what we'll do is basically do a lot of iterations and then return. We use that to make it look like it's doing some actual real work that we would have, like rendering a template or something like that, but this is easier to control, and we can define easier how many times do we want this to keep busy. With HTTP, we have a very similar setup. The main difference is that as HTTP is using a different way of running, like we explained at the beginning of the talk, we only need 4 workers because it wouldn't make sense for us to have more workers. It would be counterproductive. We just want 1 worker per CPU. Leaving that aside, it uses Unicorn, and everything else is exactly like the Flask application. For the I/O handler, the code is slightly more complex than with Flask. Instead of doing directly request.get, we will have to initialize the client session. In this case, we want to do up to 10,000 concurrent requests per second, so we have to define that. And then we will need to use asynchronous context managers to actually do the call. But if we forget about this minor implementation detail, it's exactly the same code. Any questions so far? Is this clear? Can you read it? For the CPU handler, the code is exactly the same. The only difference is the way we get the parameter, because Flask and AHTTP have slightly different syntax, but that's it. So, when we discuss asynchronous and non-synchronous servers with our colleagues and stuff, I was gathering some opinions on what do we expect the async servers to behave like. And this is what we came with. It's like, okay, asynchronous servers theoretically use less memory. Well, the latency is smaller in sync servers. Sync code is simpler. Async code is harder to reason about. And asynchronous servers can handle more requests per second or have a higher throughput. So let's see how many of those are true or not. But to do that, we will take a lot of measurements. The other day I saw this in Twitter when I was preparing this talk, and I thought, that's perfect, it will go directly to the talk. So let's start with this. This is not going to be a fair fight. Flask is not going to have a happy ending in this case. It's not going to be fair in any way. So if you wanted fairness, please leave. That's not going to happen today. So, response time. Here we have 5 examples. The first one is a hello world, so no delays, nothing. It's just a sample page without nothing in it, no delays. It's the simplest you can get. And as we can see, The fastest one is Nginx, no surprises here, then HTTP, and then Flask. I was kind of surprised by this because HTTP is actually faster than Flask for synchronous requests. Then we have the CPU waster. The CPU waster is the busy loop with iterations. We don't have an Nginx column here because Nginx doesn't let you add this kind of busy loop, but we have this example, and we can see that HTTP is actually faster than Flask responding to these connections. When we start getting delays, we have the Nginx columns as a baseline to know what's the maximum performance we can expect. We can see that the performance is similar in the same order of magnitude, but the HTTP tends to perform a little bit better, except in the case with 1 second where Flask is more or less the same. But what's the main difference? Because if we think about it, okay, the results are more or less the same, but is it worth it? Let's see how many requests per second we can get. This was very surprising to me. HTTP is actually faster than OpenResty with Lua. I don't know how to explain that. If someone has some idea of why this might happen, I'm pretty open to discussing it. It was really interesting. With the delays, we can see that the performance is quite similar between HTTP and Flask. So again, no real gains here, nothing interesting. But here comes the interesting part of it. In order to be running HTTP, we only need 4 workers. In order to get this kind of performance with Flask, we need 100 workers. What does it mean? What does this mean when it comes to memory requirements that we will have in our application? It means that Flask will take 25 or 50 times more memory than it would take to actually run the same application in HTTP for a very, very slight increase in code complexity. As we have seen the both examples, we can see that really the difference in code is negligible. It's really easy to compare one code base to the other. So even if it is slightly more complex, the memory gains that we get out of this are incredible. I was trying to get logarithmic differences between these, and it didn't look good because HTTP is basically in the negative values. And it didn't even give us a clear picture of what's going on here. The differences are so big that it's outrageous. So let's revisit the assumptions that we had some time ago. Asynchronous servers do use less memory. That's true. Latency is not smaller in sync servers, at least not in these tests. That was surprising to me. I always expected that this would be the other way around, but I got with it. I got with these results. Sync code is actually simpler, as you have seen. Slightly simpler at least, but let's give some points for Flask. Asynchronous code is harder to reason about. That's true. It will be harder to actually profile your application. It will be harder to test it. It will be harder to trace your app code because the workflow might be interrupted in the middle of the request, and the logs will be harder to read. Then asynchronous servers can definitely handle more requests per second given the same machine specs. That's clear if we look at the RAM requirements that we have here. So, I think I've gone very, very, very fast. I'm so sorry about that, but we can spend some time with questions then, I guess. So, what are asynchronous servers great for? If you have slow dependencies, that's a no-brainer. Flask will be using 25 megabytes of RAM for every request that you have. You don't want that at all. So, please use asynchronous servers if you need to fetch data from a very slow API or a database that needs to do a very long query. The memory savings will be significant. Same thing if you have many external dependencies. It's very easy to multiplex your dependencies so you can grab them in parallel, speeding up your application. Nathan was doing an example before where he was fetching 5 or 4 URLs at the same time. With Flask, you would need to do this with threads, and it gets complicated. Threads are expensive to create. If you were doing this with async.io, it gets much faster, easier, and at the same time, you don't have to go to the kernel to ask it to actually create a new thread. So it's a win-win situation. You will always be faster. If you want to aggregate data from multiple sources, again, it's a very good fit. If you're working with microservices that talk HTTP to each other, it's a natural fit. And if you're doing lots of I/O of any kind, it also works very well for the same reasons. Asynchronous, it tends to be bad for static content. That's not incredibly true, but with Python applications, if you're just serving static traffic, you might not want to go with HTTP. But again, you should be using Nginx or something like that, probably. If you're doing CPU-intensive work, that's not a good fit either. What you can do if you want to use asynchronous servers is offload your load to using Celery or something else. You just put the tasks there, you get your workers to do the work, and then when the information comes back, you display this information. So you can still do that, but if you blow, what's going to happen is that all your requests will suffer for it, and your clients will start seeing the delay, and you don't want that. You will have lower memory footprint if you use asynchronous servers most of the time, and you will get higher throughput with the same machine specs. On the other side, latency can be higher in some cases, not always, and chasing bottlenecks for asynchronous applications is harder, especially if you need to chase your libraries if they are not well written. And that's all I have for now. All feedback is welcome. You will have the code samples if you want to reproduce these results in this URL. You have the QR too. And if you have any questions, I will be happy to answer anything you want.
So we've got plenty of time for questions and even discussion.
Oh, come on, we have 15 minutes. Please say something.
I guess I'm curious about something. So for the Flask setup, you did 100 workers or 100 threads?
100 workers.
So how does Unicorn do that? Is it just one process per worker?
Yep.
Okay. So it's not doing the threading on the process. It's just doing a single threaded process for each of those.
I think so, yeah.
Okay. It might be slightly faster if you did 2 threads per process or something like that. But
yeah, I don't really know how the Unicorn threading model works.
and I guess and with that is I thought I read that Unicorn's slightly slower at serving AIO HTTP as well. So you might also get better performance if you just went with raw AIO HTTP.
Yeah, definitely. The thing is that doing it with Unicorn, I was getting something out of the equation. So we have Unicorn in front of both services. So I'm kind of not giving an unfair advantage to HTTP because there's an extra step in the middle. So I thought it will make it more fair.
Right.
Even if it's not very fair, as you said.
If I may, I would like to add a couple of comments also. First of all, regarding the thread and the contention of the GIL, I think it's worth it to mention that the Python interpreter automatically releases the GIL when there is a network operation. That's important because when you have just a few of threads, you shouldn't pay the contention in this operating system. Therefore, the GIL is a pain, but it's a pain when you have many threads. This is automatically handled by the Python interpreter. And also I think it's also worth it regarding the memory. It's about the Python by itself as an interpreted language. We cannot use the copy on write system in the kernel. It means that every time that you fork a process in Python, it basically creates many dictionaries that in fact are code, because each dictionary is referenced in the garbage collection. All of the pages that belong to that page that means for code, they are duplicated.
Yeah.
Therefore, we are wasting a lot of memory every time that we do a fork in Python. Just a couple of comments.
Exactly.
That's one of the reasons of the memory, the problem of the memory in synchronous servers.
Yeah, exactly. Very good point. Thank you, Bob. Anyone else?